In this video, we're going to continue working examples of logarithmic differentiation. This is part 2 of the videos. So for this example, find f prime of x for f of x equals x to the 7th e to the cosine x over x squared plus 1. So notice that there's a lot of stuff going on here. We have, what do we have? A big quotient rule, and within that quotient rule, we have a product rule. So if we were going to find the derivative of this, doing it as it stands, I will say, okay, so it's the derivative of the bottom, sorry. So it's x squared plus 1 times the derivative of the top, e to the cosine x, and then we have a chain rule in here as well, right? E to the derivative e to the cosine x. I will have to figure out that chain rule. So low d high minus high, so x to the 7th e to the cosine x times the derivative of the bottom, and then all over the bottom square. And so this, while it doesn't seem too bad, now here the derivative of x to the 7th times cosine x, we need to use the product rule there. And when I do the derivative e to the cosine x, I need to use a chain rule there. So this problem has all kinds of characters showing up. So another thing that we can do, because this is starting to look too complicated, is I can say we're going to use logarithms to rewrite. So this is what we're going to do. So instead of, so I know that f of x is just a fancy name for y. So instead of calling it f of x, we're going to call it y. So I'm going to say y equals that, and I'm going to take the logarithm of both sides. So take ln of both sides. Now remember, logarithms are functions, so you're taking ln of something. So when I take ln of both sides, it's kind of like when you take the square root of both sides, right? The square root is a function, so I'm not multiplying. So this is going to become ln of y equals ln of all that stuff. Why am I taking the natural logarithm? I'm taking the natural logarithm so that then I can use the properties of logarithms to rewrite the right side. So now we're going to use properties of logs to rewrite, which is going to be much nicer than taking that quotient rule embedded with the product rule embedded with the chain rule. So I'm going to take the derivative after I'm done rewriting. So now let's rewrite. So the left side stays ln of y. The right side, now I have the division, so I can say this is going to be the ln of x to the 7th times e to the cosine x minus the ln of x squared minus 1. And I have a product here. This is the same problem that we did in the previous video, so we can rewrite what we did, but I'm just going to go over it again. So ln of x to the 7th plus any product becomes the sum of the two logs, so natural log of e to the cosine x minus ln of x squared minus 1. And now we can use the property of logarithms. Notice that I am still rewriting. I have not taken any derivatives yet. I'm still just rewriting. So, and I'm going to rewrite one last time to bring those exponents down. So this will be 7 ln of x plus ln of e to the cosine x is just cosine x, right? The ln is log base b, and minus ln of x squared minus 1. Now notice here I'm not doing anything with this because our rules of logarithms, where were they? I wrote them somewhere. Here they are. Notice that the rules of logarithms only have, it's a single, when it's a single logarithm, we have product, we have quotient, and we have powers. There's nothing that when you have a single logarithm that has a plus or a minus inside that tells us what to do. We have pluses or minuses when we have multiple logarithms. So back to this example that we're working with, right? There's a single logarithm here, but I don't have a way to expand that. So be careful not to say ln of x squared minus ln of 1 we don't have a way to expand addition or subtraction inside a logarithm. So this is as far as we can go. So now I can take the derivative. Now that I'm done rewriting, we're going to take the derivative. So when I take the derivative, ln of y, right? Y is f of x. So derivative of ln of stuff is 1 over the stuff times the derivative of the stuff by chain rule equals, and then take the derivative of this side. So that would be 7 times 1 over x. The derivative of cosine x is negative sine x, and the derivative here, we have another chain rule, ln of stuff is 1 over stuff times the derivative of the stuff. And then just finish rewriting it. So I have 1 over y times y prime equals 7 over x minus sine x minus 2x over x squared plus 1. Am I done? Not quite. I need the y prime all by itself. So isolate y prime. How do I isolate y prime? Multiply both sides by y. So I'm going to have y prime equals y times this. But what was y? Y was the original function, right? We called it y, but it was our f of x, which was x to the 7th e to the cosine x over x squared plus 1. So that is my what y equals, and then times the derivative that we found. So which one is better? You be the judge of that. I think it's easier to do it by applying the rules of logarithms than having to do a quotient rule. So what we were doing here, a quotient rule, and then in taking the derivative of this, I would have had to do the product rule embedded with the chain rule, and then I will have to multiply that out quite extensively in order to simplify. So I prefer the logarithmic differentiation. Apply the log to both sides. Logarithmic is a function, right? The logarithm is a function. So apply the logarithm to both sides and then take the derivative. So let's try another one. So I'll give you this one to try on your own. Pause the video, try it on your own, and then unpause and see the solution. So here's the example. So as you work on it on your own, I want you to think about what would you need to do if you don't use logarithmic differentiation, and then try using logarithmic differentiation. So take the natural log of both sides, and then what rules of logarithms do you need to rewrite it and simplify it. So go ahead, pause the video, work it on your own, and then come back and do it together. All right, so now that you have worked on your own and unpause the video, let's keep going. So this, you can rewrite it as x plus 1 over cosine 5x to the 1/2, right? That's the square root, so we can write it to the 1/2. And so this is a great candidate for logarithmic differentiation because I have a power, I have a quotient, I have all kinds of good stuff going on. For logarithmic differentiation, if I don't use logarithms, then I have a chain rule embedded with the quotient rule and another chain rule in there. So I am going to use logarithms. So take natural log of both sides. So I'm going to have the natural log of, I'm going to leave it as f of x, I'm not going to change it to y, equals then the natural log of this stuff. And why do I take the natural log? Because now I have a logarithm and I can use properties of logs. So use logarithmic rules to rewrite. So let's see, what does that look like when I rewrite? So the left stays the same, and the right, the exponent, we can bring it to the front, so it'll be 1/2 ln of the stuff. And now I have a quotient there. So I can say 1/2 in brackets here because I'm about to expand a single logarithm into two logarithms, right? I have a numerator and a denominator. So it's going to be ln of x plus 1 minus ln of cosine 5x. Can I rewrite some more? And no, right? So my caution here right, the ln of x plus y is not equal to the ln of x plus the ln of y. That is not a property of logarithms. You cannot expand when you have plus or minus inside of a single logarithm. So this is as far as we can go in terms of rewriting. You can distribute that 1/2 if you want, but I'm just going to keep it on the outside. So now let's take the derivative. So differentiate both sides. So when I take the derivative of both sides, what do we get? ln of stuff is 1 over the stuff, so 1 over f of x, times the derivative, so times f prime of x, equals the constant that kind of hangs out. ln of x plus 1, derivative of ln of stuff is 1 over x plus 1 times the derivative of the inside, but the derivative of that is just 1, minus ln of stuff, 1 over the stuff, so 1 over cosine 5x, times the derivative of that cosine of 5x. The derivative of cosine is negative sine of 5x, and this has an embedded chain rule in there, right? So the derivative of 5x is 5, and those are times. And so let's rewrite it. So I have 1 over f of x times f prime of x equals 1/2, and this is just 1 over x plus 1 minus times, we're multiplying these. Minus times a minus becomes plus sine 5x over cosine 5x, that's tangent of 5x, and then times 5. So I'm going to put that 5 up front, and that is it. Well, almost. What do we still have to do? Isolate the f prime. So f prime of x, multiply both sides by f of x, so it'll be f of x times, and now if you want you can bring that 1/2 or you can leave it there, and then we're just going to be 1 over x plus 1 times, or sorry, plus 5 tangent of 5x. How did I get the tangent? Sine over cosine. How did this become plus? You have a minus, and the derivative of cosine is negative sine, so that's why you have a minus, and these are being multiplied. And what was f of x? F of x was our original function. So my final answer is going to be replace the f of x with what it was, which was the square root of x plus 1 over cosine 5x. And then you're going to have times, I guess you could put that 1/2 at the front. I'm just going to leave it the way that I have it here. Phew! So that will be that derivative. So you can try on your own doing it the long way, right? Which is the going from here and doing the chain rule. So it'll be 1/2 this to the negative 1/2, and then times the derivative of the inside. The inside, you need a quotient rule with that built-in chain rule in there. I guess another way you could have written this is that notice that you have x plus 1 over cosine, but 1 over cosine is secant, right? So you can say this is x plus 1 times secant 5x, the whole thing to the 1/2. So we could have also done it that way. And so this, using the properties of logarithms, this will become a natural log of x plus 1 plus natural log of secant x instead. But in the end, we should get the same answer. All right, lastly for logarithms, what I wanted to talk about is, and summarize, what do we know so far? So far I know that if y equals ln x, then y prime is 1 over x. And then if I have a chain rule, So if I have with chain rule, that means if I have y equals ln of g of x, then the derivative is 1 over g of x, right, 1 over the stuff times g prime of x times the derivative of the inside. So that's the gist of the chain rule. We also know, so with exponentials, what did we do with exponentials? Exponentials are the inverses of logarithms, so I know that if I have y equals e to the x, the derivative is e to the x. And last time we also learned that if y equals b to the x, what was the derivative of this? What's y prime? This is b to the x times the natural log of b, right? So if I had y equals 7 to the x, what's the derivative? Y prime is 7 to the x times ln of 7. And then if you have chain rules in here, like b to the f of x, 7 to the f of x, then the chain rule applies. So this is what we did with exponentials. So now that we have logs, the logarithm is the natural logarithm, the inverse of e to the x. What about a general logarithm? Something with the base b. So if y equals log base b of x, then what is y prime equal to? We are going to use our definition of logarithms again and implicit differentiation to do this. So we're going to go back and use log base b of a equals x means b to the x equals a. And so here I'm going to have b to the y equals x. And so what we're going to do, that's using the definition here. And now we're going to take the derivative of both sides with respect to x. So what am I going to have here? So I'm going to have the derivative with respect to x of b to the x equals the derivative with respect to x of x. And so what's the derivative of b to the x? We just wrote it up here as we were reviewing. The derivative of b to the x is, you get the exponential back times the natural log of the base. Oh, that's not x, that's a y. B to the y, right? That's what I'm using. So here I'm going to need then the chain rule because I'm taking the derivative implicitly. So remember that y is a function of x. So when I take the derivative, I'm going to have, what are we going to have? We get the exponential back, so I'll get b to the y times the natural log of the base, but by chain rule, times the derivative of that function times y prime equals the derivative of x with respect to x is just 1. And so solve for y prime. So how do I get y prime by itself? Divide both sides by b to the y ln of b. So I'll be left with y prime equals 1 over b to the y ln of b. But what was y? Y was equal to the log base b, right? So then this is b to the log base b of x times ln of b, but bases are the same, so I'll just get x. So this is 1 over x times ln of b. So what does this tell you? Therefore, for y equals the log base b of x, what can I say about the derivative? Y prime is 1 over x times the natural log of b. So notice that for the way I remember is that when it's an exponential, you get the exponential back, so it's b to the x times the natural log of b. For a logarithm, the derivative of a logarithm is 1 over x, right? 1 over whatever the function is. So ln of stuff, 1 over the stuff times the derivative of the stuff. So even if the base is different, when y equals log base b of x, I still am going to get 1 over x, but now I'm also dividing by the natural log of the base. So an example here is find the derivative find dy dx for, say, y equals 5 to the x. So I know this is an exponential, but just reviewing exponentials, what's the derivative of this? So the derivative of this will be, you get the exponential back times the natural log of the base. So what if you have find dy dx of the logarithm? So for log base 5 of x, for y equals log base 5 of x. So now I can use this rule up here, that if I have the base is different, right, not the natural log, so not log base e, when I have some other base, is 1 over the inside, so 1 over x times the natural log of the base, so, or divided by the natural log of the base, whichever way you want to think of it. So y prime then is going to be 1 over x, because I just have an x there, natural log of 5. Sometimes you might see this written as 1 over x times 1 over the natural log of the base. So you can think of it this way as well. So what if we have a chain rule? So with chain rule, let's say y equals the log base 2 of x cubed plus 1. So what is the derivative of that? So go ahead and try it on your own, see what you come up with. Pause the video and then come back and do it together. So y prime is, so ln of stuff or logarithm of stuff, the derivative is 1 over the stuff. So I'm going to get the x cubed plus 1 times 1 over the natural log of the base, and then, which is 2, not b, and then by chain rule, times the derivative of the inside. Right, so that's what's happening over here. So the derivative of the inside is 3x squared, so I'm going to say 3x squared over x cubed plus 1 natural log of 2, and so that will be my derivative. So when the base is something other than e, if it's not the natural log, if it's some other log, then you have to do times 1 over the natural log of whatever the base is. So let me rewrite all the stuff. So what we know is, so let me do as I've done before with other functions. So all of our, so if this is our function, then the derivative, right? So if I have the natural log of x, the derivative is just 1 over x. If I have natural log of a function, natural log of stuff, that's a g, it will be 1 over the stuff times the derivative of the stuff, and you might see it in your book as g prime of x over g of x. And then when the base is something else, right? So if I have the log base b of x, then the derivative is 1 over x times 1 over the natural log of the base. And if you have with the chain rule log base b of g of x, that's a g, then the derivative is 1 over g of x times 1 over the natural log of the base, and then times g prime of x. So you might see this in your book as g prime of x over g of x, and then times 1 over the natural log of the base. So those are the big things with logarithms. Contact me if you have any questions.